Good afternoon, everyone. Welcome to the third Library Lunchtime lecture for this semester and the last one for this academic year. Our speaker today, Associate Professor Ulrike SALZNER from the Chemistry Department, will give us a tasty talk on chemistry and cooking. She tells me that she has a lot to get through, so I shall just kind of cut short my introduction so that we don't run over too much and we may have time for some questions at the end. Just like to say that Dr. SALZNER's talk today grew out of a discussion we had over a dinner, in fact, at the beginning of the semester when she was explaining that she's teaching a course on food chemistry to students in her department. And obviously that has a potentially broader appeal, so we thought it would be nice to invite her to speak at the library. So without any further ado, and I'll miss all the details that I had planned, I shall hand you over to her. Okay, thank you.
So thank you. Thank you for the introduction, thanks for coming, and thanks for the library team for the organization. So I have, this subject came out of a discussion with students actually. For 3 years ago, some students approached me and they said they would like to have such a course. And I had a long-term interest in cooking, and I had already books on food chemistry and so on. I said, sure, I'll make such a course if our department wants to do it. So this is a little short version of it. So I have put here on the starting picture just, this is sugar, all kinds of white and brown sugar, and this is what happens when you heat it. It decomposes, so organic material, and it decomposes, and you get all these molecules here. This here, for instance, is ethanol. This is alcohol. That's what we are drinking. There is one here. This is a diketone. This is a flavored taste of butter. And if you fry a steak, then you get compounds which contain nitrogen and sulfur, and they make the meaty aromas. Now, our food, in principle, the bulk of the food is carbohydrates, fats, and proteins. Now, if you heat the sugars, they decompose. If you heat the fat, it melts, but by far the most interesting are the proteins. There's much going on, and for that reason I choose for the topics in the talk, cooking meat, proteins. This will be the bulk of the whole talk. Then a little bit about artificial sweeteners. There's also an interesting story about that here, and a little bit about food additives, because people have such a negative attitude towards chemistry and food additives, so I want to clarify a few points and explain a little bit what's behind that. So let's start. How did it begin that we're eating meat and that we are cooking it? We have evidence that people used fire about 1.8 million years ago. And at some point somebody must have come up with cooking. We don't know why, but it could be, for instance, that maybe there was a bushfire, maybe some animal died, maybe it was half cooked or fully cooked, and somebody ate it anyways. And then the question is, did they like it? If they're used to raw meat, maybe they didn't like it at first. But what happens during cooking is that the meat becomes more digestible, the nutritious value becomes more easier to gain to the body, and we have a taste for everything which gives us calories. We like it. We like proteins, we like sugar, and we like fat because it gives us calories. So probably the feedback cycle that this is good was very fast, and people started cooking. Now these guys, let's look at a piece of meat on a fire. These guys definitely had no clue what meat is made of. There was no chemical analysis. We have a fire. The flame of a fire is about 1,000 degrees. So you're starting, you look at this. This starts from a raw red meat. It changes color. It shrinks. It develops a brown crust. Something's dripping in, burns, smokes, comes up, ends on the meat. Nobody knew what it was. And then they pop it in their mouth and eat half a kilo of it. Imagine you go in a lab, you take an unknown substance, you make all kinds of possible chemical reactions, and then you eat half a kilo of it. What an experiment. So that this was a success is actually a surprise. I mean, it was luck. And it was a success story. So some people who are really passionate meat eaters, if you put a salad in front of them, they're not looking very happy. So meat eating has become a huge success in our culture simply because it gives us a lot of nutrition and makes us feel good. Well, let's look what is in a meat. So this is an entrecote steak here, which I bought and photographed. So what's the main component of that? Anyone knows what's the main component of meat? No, huh?
Water.
Very good, water. The main component of meat is 65 to 75% of water. That's what we normally don't think of first, but if you're a scientist, you might have some background information. Yes, most of it is water, and then it comes protein, 20%. The main part of the protein is muscle fiber. These are very long fibers. So, too much, wrong part. Very long fibers, and then we have also connective tissues which keeping the fibers together. Main of the connective tissue is collagen. And collagen is actually the main protein in our body. It's all the tendons, ligaments, holding the fibers together and so on. Collagen makes our skin look good. When we age, the collagen gets less in our body and we get wrinkles. So collagen is very important and it holds the meat together. And then we have fat. This is seen here, is called marbling. So here are big fatty splotches and there's a little bit in between. And the fat is good for the meat because it makes it feel more juicy when we eat it. What's not shown here, we have also in the meat some sugar. There is some glucose in the meat because the muscle fibers, in order to move, they need energy, and they stored glucose and some glycogen, which is a polymer of glucose. So this is also in the meat. So if we are now starting to cook this, we will apply heat. We start doing chemical reactions with this. And the first thing which is important about the water is that if you heat water, it cannot reach more than 100 degrees. It starts boiling, and when it boils, all the energy goes into evaporization, and the water stays constant at a temperature of 100 degrees. The same will happen in the meat. So unless we are drying out the surface and have all the water off, the meat will be at 100 degrees, and we can only boil it, but we cannot fry it. So this is another picture of the meat fibers bundled up, hold together with collagen. And here's another protein shown, which is myosin. This is responsible for the red color of the meat. This is similar a little bit to hemoglobin. Hemoglobin transports the oxygen in our blood, and then it transfers the oxygen to the myosin, where the red muscle fibers can store it. So red muscle fibers store oxygen. White muscle fibers, like in chicken, they store less oxygen. This is red muscle fibers are for long endurance motion, walking and constant motion, and white muscle fibers are for rapid motion, for instance, fleeing. When a bird has to quickly run away from a cat, flying up in the air, these are bursts of energy. The muscle mobilizes, there are more strength, but it cannot endure because it cannot store enough oxygen for such a motion, so it is going without oxygen, and then it causes sore muscles, and the muscle gets tired. So this is in principle the structure in a cartoon-like. We have the meat, we have the long muscle fibers, and what's very important, these muscle fibers, they can contract. I mean, this is when I move my arm, I'm contracting my muscle fibers, but they can also contract when the animal is dead. The first thing is the muscle fibers contract after slaughtering. This is called rigor mortis, and it makes the meat tough. When you fry meat, when you heat it, these muscle fibers contract, and then they squeeze out the water, and then the meat becomes dry. So on the surface, that's good because then we can create flavor, but you don't want the whole meat dry because it will be terribly tough and you can't eat it. It will not be fun. So since meat is made mainly of proteins, these muscle fibers are of proteins. The myosin is proteins, the collagen is proteins. I have to torture you a little bit with proteins. So if you're not a scientist, we will do it slowly. What I'm showing here, this is a so-called amino acid. Now, we have here N means nitrogen, C means carbon, O means oxygen, and H is hydrogen. So this is, every little ball here is one atom of this element, nitrogen, carbon, oxygen. So amino acid is a relatively small molecule. We have only 4 elements in it. And here this R is an abbreviation for some kind, it's called organic residue. It can be CH3 or something a little bit bigger. And we have then totally in nature about 20 amino acids which occur in natural products. So they are differing by this R group, but all the essential thing, NH2, this is the amino group, and COOH, this is the acid group. All of them have it. So this is our amino acids, and the proteins are made of amino acids in the following way. We put another one, exactly the same amino acid, and then you see here this part here. If you put this together, this is 2 hydrogens and oxygens, H2O, that's water. So if you split up one molecule of water, combining these 2 molecules, then what's left here is CO and NH. And here we are forming a new bond and water goes out. So now we have formed a molecule of 2 amino acids. And you see here the CO group is here. And the NH group, which is left behind, is here. And we have a new bond between the 2. So this is a dipeptide, and this kind of bonding is called a peptide bond. Now, obviously, if I put another amino acid there, I can do it again. And I can do this many times until I get a polymer. So proteins are polymers of amino acids. That's what they are. As I said, we have 20 different amino acids, and we can make long chains. They can be thousands of units. And it can be a mixture of all the 20 amino acids in any kind of random order, and then you have, of course, a huge amount of different proteins. Now, on the next slide, every one of this group, NH, will have a little circle like here, but it will mean an NH group. The CRH group will be one colored circle, and the CO group will be one colored circle. So there will be 3 colors for these 3 groups, which repeat each other. Okay, this is shown here. As you see, CRH is blue, CO is orange, and NH is white. And we make now a long chain of these amino acids. And now they have an interesting property. They are rolling or going up in a helix. This is called the so-called alpha helix. And what's the importance for cooking here is that such an amino acid chain is relatively stable. These are covalent bonds, and they can take a lot of punishment. So you need to heat them well above 100 degrees to do anything to it. But these connections here, which are dotted, they are very weak. And they are starting to decompose at around 40 to 60 degrees, depending on the protein. Then this structure gets destroyed. So that's not yet the end of the story. There's again the alpha helix here. Now you can roll this whole thing up, folding it one more time. You see the alpha helix is in here. And then you have the so-called tertiary structure of the proteins. And then you can take these lumps here and cluster them together, different proteins mixed, and then this is called a quaternary structure. So primary structure is the amino acid sequence. This is quite stable. Secondary structure is connected weakly. Tertiary structure is folded up, can also be changed relatively easily. And the quaternary structure is a cluster of different proteins. This one here is hemoglobin. You all have it in your blood. So when we are cooking, what happens is that we are destroying the tertiary and the quaternary and the secondary structure. This is the main thing when you cook. When you boil an egg, for instance, these proteins will start unfolding because you're adding heat to it. And at around 60 degrees, all these proteins will then make a 3-dimensional network, because if you think that here are weak connections between these amino acids, when you put 2 proteins next to each other or across, they can make such connections also, and then you form a 3-dimensional network, and then it becomes solid. So when you boil an egg, you unfold the proteins in the egg and make a 3-dimensional network of protein chains. And that is exactly what a cooked egg is like. The collagen is also a protein, but it's a little bit different one. It is, of course, a sequence of amino acids. It's in our bones, tendons, and so on. And this collagen, well, we don't have to care what amino acids it's exactly, but we have 3 strands which combine in a triple helix, looks like this. So 3 protein strands together, and then thousands of them form fibers. And these are very strong fibers, which are our tendons, which connect the muscles to the bones. And it is also holding the muscle fibers together. Now, if we are boiling collagen, if you are heating it to about 70 degrees, then this triple helix comes apart, and we have individual protein strands. This is gelatin. And gelatin, if you cook a chicken stock and you put it in the fridge, it becomes solid. And this is the gelatin which makes it solid. So we are unfolding the collagen. The meat which was tough because of the collagen becomes soft. And when you cool it down, you get a three-dimensional network of protein chains like in the egg, and you get a solid. So when we are heating collagen, it partly dissolves into the sticky gelatin, and the gelatin becomes softer during cooking while the muscle fibers contract and become tougher. Young animals have only a little bit of collagen, and it dissolves well. They have a lot of collagen, but it dissolves very easily. This is why young animal, veal for instance, is much more tender than an old cow. Older animals with well-worked muscles have done a lot of work on them. They have strengthened their collagen, like we are all tennis players. We are very tough. And, well, old cows are tough. So the other component is fat. The fat has the advantage in the meat. First of all, it dissolves the flavors, and the flavors make the meat tasty. This also contains the differences between, for instance, sheep, cow, chicken, and so on. They have different flavor components, and the difference in the taste in the meat is in the fat. It can be under the skin, it can be around the organs, and it is also in the meat. Marbling, I have mentioned it, it's in a steak as well. And if you have fat in the meat, it appears more tender because first of all, it disrupts the muscle fibers. Second, it melts while frying, so it lubricates the whole thing and it gives an appearance of more tenderness and it makes it more tasty. So you don't want to have too lean meat if you want a good food. So when we are frying meat, now what happens is, if you put it in hot oil, at first the water starts evaporating from the surface. And so the moment the surface gets dry enough, then it gets hotter, the temperature starts rising, and then we can get the browning reaction, which makes the flavors. At the same time, if you reach only 40 to 60 degrees, so this is way before that, the proteins denature, as I said, triple helix, helices decompose, secondary, tertiary structure changes, color changes because we are destroying the myosin, which makes it red, so the meat becomes gray. Muscle fibers and collagen contract and squeeze out water like a sponge. This meat becomes drier. Around 70 degrees, the collagen dissolves and the meat becomes, because of that, softer. The fibers fall into bundle. For instance, if you make a stew and you cook it longer time, then you see these meat fibers and they're falling apart. That is a different kind of tenderness. This is when the collagen is dissolved, but the muscle fiber is still intact, and the individual fibers are relatively tough actually. Above 100 degrees, finally we are getting what's called a Maillard reaction. This is a reaction between the sugar in the meat and the protein, and that makes the flavors. So we have actually different temperature ranges, and to cook a really good meat, we have to be really careful with that. Heat it too high, it's all tough. Heat it too low, you have no flavors. And everyone who makes beef, which is probably the most difficult to cook, might have one time had a bad experience with it. So the Maillard reaction is a chemical reaction which produces all the good things we eat. It makes the bread crust, it makes the steak crust, and it is a reaction between the protein again and the sugar. So I haven't shown sugar structures, they're a little bit big, but what we need to look at is this group, CHO. This is the aldehyde group in the sugar, and this one reacts with the protein in the following way. Here's the HCO group, aldehyde group, and here's the protein, the NH2 group, and here they're making a connection. And then they make rearrangements, and then if it's hot enough, hell breaks loose. I mean, they are getting, you have 20 amino acids, you have different sugars, you have a high temperature, chemical reactions all over the place, you get hundreds of chemical compounds. There are huge articles about it, analyzing these things. Nobody knows all of them. It's very difficult to even separate them. So why is it difficult to cook a good meat? Because we want to make it tender in juiciness, we want to have it cooked evenly, and we want to have the flavors. So to create the flavors, we need over 100 degrees. 154 is ideal. Then you have the Maillard reaction going at full speed. Make it tender needs only 70. So we are getting this. But the moisture loss starts already at 55 to 60. So we want to keep that at a minimum. But how do you keep the moisture loss at a minimum while creating the flavors? That's the difficult part. So one has to choose a compromise for the kind of meat. For instance, if you have a tenderloin, which doesn't have much collagen, then you fry it quickly in the pan, make it very hot from outside to get the flavor, and if it's thin, it's actually finished. If it's a big piece, put it in an oven at a low temperature and just cook it very gently all the way through, and it will be juicy. If you have a tough meat, this is better for a stew because it needs long cooking to get rid of this collagen. And then you have to make the compromise to lose some more moisture. And the funny thing is you can get dry meat cooked in water because you're squeezing the water out of it. So the chemists got into the business actually some time ago. One very famous one is Justus Liebig. He is a very famous organic chemist, and the university in Gießen is named after him. He organized organic chemistry. He devised modern laboratory teaching techniques, and he's called maybe one of the best chemistry teachers of all times. He's called as a father of fertilizer industry because he discovered nitrogen as an essential plant nutrient, and he developed the bouillon cube. He was thinking that the main nutrition in the meat is in the juices, and he extracted the juices. They started a company with carcasses which were in Argentina. They slaughtered the animals for the hides and let the meat rot. And there he got a cheap meat source for making meat extracts, and so this was his thing. But he had one claim which is interesting to us. He said if you fry the meat very hot, you can seal in the juices and the meat will be juicy. And you have this in many cookbooks to this day. Now there is on the internet, many cooks have said nonsense. You cannot seal in the juices, the water will come out. And on the internet are now claims that debunking the debunking and saying no, you can seal in the juices. So what can we do to test such things if we have contradictory information? Best thing is to try it ourselves. So let's design an experiment. We have a hypothesis, or we want to test something. Are the juices sealed in frying hot? Yes or no? Let's make an experiment. Take 2 pieces of meat, make them equal weight. 135 grams I used. Take 2 equal pans, fry one with little, we put a bit oil for heat conduction. We put one on a flame on full heat, one on low heat. Make it one with relatively cold pan, one with a very hot pan. Fry them and weigh them before and after. Then let them sit after that and see whether the juices are coming out, yes or no. Okay, let's go. Here are the meats. Rump steak, noir rosto. Actually a little bit too lean for enjoying it, but it's a nice meat. 2 pans, stove, one on full, one on low heat. 2 minutes from each side, 4 minutes total cooking time. Okay, putting it in. Now you see, this here is the hot pan. You see here smoke. This means the smoke point of oil has reached. This is sunflower oil. It has a smoke point, means the point where the oil starts to decompose, 220 degrees for sunflower oil. So this is a very hot pan. This is the low pan, and you see here some juices coming, right? It's wet. This one looks dry. We keep going. It's smoking a lot. Normally I would turn this down, but for the sake of science, I had to sacrifice the pan, and we have cooked it longer. So you see again, here it's dry, here it looks wet. I'm telling you, weighing before and after showed very clearly this steak lost more moisture. Clearly it's hotter, more water evaporates. What happens here is this pan is not so hot, the water evaporates more slowly. And this is why we see it. And in this very hot pan, it goes up into vapor immediately, and you don't see it. So then, flipping it over, you see here the beautiful products of the Maillard reaction. Here is very little. And we finish the 2 minutes, smoking. And that's the steaks afterwards. And this one looks better, I must say. And then, so we had, I weighed them. The hot steak lost 10 grams, the cold, less hot fried steak lost 7 grams. That's a difference in moisture loss of almost 50%, 7 to 10. As I said, that it looked different in the pan is simply the water evaporates slower in the colder pan. And then after standing, you see this puddle of, and here's almost nothing. So clearly, this steak lost more water. You cannot seal in the juices. So what we said before, more liquid is lost, Liebig's claim is wrong, and you can try it yourself. I mean, of course, one should not try it only once. Scientific experiments have to be done a couple of times, but I think it will work again. The observation is that the muscle fibers contract upon heating, and they squeeze out the water, and you cannot seal in the juices. If you fry meat too high, too hot, it becomes dry. That's the conclusion. Cutting it in half, you see that this meat is not cooked. Okay, it's raw in the middle. I measured the temperature 46 degrees. It was not cooked enough. So you would, actually what I did with the meat, I put it in the oven at 100 degrees, let it very slowly finish, and I ate both of them, and they were very good. So the result, cooking the meat leaves the meat actually in the middle raw. Frying it longer would squeeze out more juice. This is why I made it in the oven at low temperature. But there were 3 mistakes made in this experiment if you want to make a good steak. First of all, it was the wrong meat. This is too lean for a steak. It was too fresh. Fresh meat bought from the supermarket is usually an animal slaughtered short time ago. It was red, it was not aged. We will talk about. And it was too cold because I took it from the refrigerator. So never ever do that. I will get to this. So aging is what happens after the animal is slaughtered. So the enzymes in the meat are still alive, and they keep going to digest the meat. They start actually decomposing the meat. So aging occurs by the action of enzymes which are still alive, and they make the meat more tender and they create flavors. So a little bit of old meat is really better than fresh. During the aging, what happens is that the enzyme break down the proteins into amino acids, which have a good taste. Umami flavor is amino acid taste. They break down glycogen, which is sugar storage, into glucose, which is sugar. And also some of the energy molecules, adenosine triphosphate, will be broken down. And lipids, fat is broken down into fatty acids, and that the flavor changes. In the 19th century, it was common to leave the beef and mutton outside until it was really rotten on the outside. This was called mortification, and it was recommended by the best cooks in the world. And it makes it tasty. So one can age beef. Beef has the longest lifetime of all the meats. It can be aged for a month in the proper conditions. At about 1 to 3 degrees, because if you make it warmer, you get bacterial growth and you get food poisoning. It has to be cold. Under 5 degrees, bacteria do not grow so nicely, but the enzymes can work. And in humidity of 70 to 80%. So I made a second experiment. I took a better meat. I took an entrecôte. I left it in the fridge for 5 days. It smelled different. It was wrapped in plastic, and then I warmed it in a water bath. You can warm it on the kitchen counter. That's possible, but one has to be careful. If you put the meat out of the fridge, it warms up on the outside very fast to above 20 degrees, while it's still cold in the middle. And as you get above 5 degrees, the bacteria start growing. So it should not be done more than 2 hours, because you might have already spoilage. So I did it quickly in a plastic bag in a water bath and warmed the meat to 30 to 40 degrees. Fridge temperature is 5, so it was much warmer. And then one steak I cooked like before, 2 minutes from each side. And the other one I used the method of Heston Blumenthal, an English chef. He says flipping it every 20 seconds makes it more even. So let's do entrecôte. Looks much more, you have seen the picture of the entrecôtes. This is after 5 days. So after 5 days, you can see, actually, if you compare them, see this fat splotch, these are the same steaks. These are 2 steaks lying on top of each other here. And if you take them apart, this is the same, here, this is the same part here. You see it's starting to come apart here, also here. It's grayer, it smells different, this is an aged meat. Then putting it in the same pans, doing the same trick, and now this steak here will be flipped every 20 minutes. This will stay for 2 minutes on each side, this time full heat on both sides. Okay, this one flipping, 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 the other one is staying, so you see it gets darker, gets nice slowly, and now both of them, and this one keeps flipping until the 2 minutes are finished, and we have 2 nicely fried steaks. So they're looking now pretty much the same. Again, they were fried at high heat and they're losing water, again like before. So this is a repetition of the experiment with a different meat, different temperature. It is reproducible. Then I cut it into 2 pieces and looked at the difference. Now it's a little bit hard to see, but you see this steak, which was 2 minutes each side, is more raw inside than this one which was flipped. So this is clearly cooked more evenly. So I must say Heston Blumenthal knows what he's doing. He was right. It is cooked more evenly. This is a little bit more raw. One must admit this is a little bit thicker, but still, I think it's clear. One can see that this one is cooked through. So this is a good method of doing it. Comparing it to the first, so this is the steak which was cooked in the same way, 2 minutes from each side. You see clearly this a big difference, and this difference is the different starting temperature. This meat here was too cold, it's raw, but this one was warmed up before, it's done in 4 minutes, and you have a juicy good steak. So putting the meat from the fridge is a capital mistake. One should warm it up before, this is for sure. Getting it juicy is good to flip it over very often to get it more evenly cooked, not to have overcooked parts and raw in the middle. So that is the meat story. So, as I said, meat cooking was a big experiment for humankind. It went well, we enjoy it, it's nutritious, it's good. We have some chemicals produced in these reactions which cause cancer, this is also known, but apparently they don't harm us too much. We can have it, and actually some of the vitamins in plants, they can scavenge these compounds, and it's going quite well. So, a second experiment, I told you, I want to talk about artificial sweeteners. That is also a very interesting story. The Romans were the first, to my knowledge, who used artificial sugars. So what they did, they had substances, carunum, defrutum, and sappa. And what they used grape must. They boiled it until it was reduced to either 2/3, 1/2, or 1/3, so more boiling it in, and used this as a seasoning in their food. But there was a trick for it, a culinary trick. The best defrutum was obtained, as written in the textbook by Lucius Junius, Moderatus Columella, in De Rustica on agriculture. It's in Latin, if you're not so good as I am in Latin. The containers in which sappa and defrutum are boiled should preferably be made of lead and not of bronze. Bronze container release copper during cooking, which spoils the preparation. Now you cannot do it with pure lead, because pure lead has a melting point of 330 degrees, it will melt, but you can coat a copper pot with a lead layer, and then you get this perfectly very good defrutum and sappa. So what happens there? It is true that bronze container release copper ions, and it is true that copper doesn't taste very good, but there's more to it. Because all metal surfaces release metals, and lead containers release lead. And they are reacting with the acid in the grape juice, and they make a compound which is called lead acetate. And lead acetate tastes sweet. It's called sugar of lead. And that was the good thing of the defrutum and sappa. They had a sugar in it. So they used a sweet sauce on it. But lead, of course, is very poisonous. It's a nerve poison. It goes into the brain, into the bone, and everywhere, and it does a lot of damage. So there were people who realized that this is not good. Wine sweetened with defrutum was so popular in ancient Rome that Plinius complained. Natural, unadulterated wine is unavailable nowadays, even for the higher class. So much poison is added to wine to adjust it to our taste, and then we are surprised it is unwholesome. So the Romans had a clue that the lead was not good for them. But it was the time before the European Food Agency who tested these things, and people were more on trial and error. So what is it? Here we have another recipe here, flamingo with defrutum. Fry the bird, mix crushed pepper, ligusticum, celery seeds, roasted sesame, parsley, mint, dried onions, honey, licamen, this is a fish sauce, vinegar, oil, and defrutum. So they cooked a lot with it, and they definitely got themselves a good lead poisoning. So we have Pope Clement died in 1047, and it was always suspected he was killed. They found enough lead in him. He did die of lead poisoning. Whether it was murder is not clear, because it was used at the time in paints, in wall paints, in water piping. The PB symbol means plumbum in Latin and gives the English word plumbing. Plumbing comes because piping was mainly made with lead. So this is the origin of the word plumbing in English language. So it was everywhere. It was in the water piping, it was in the cooking pots, it was in sealing bottles, it was on rooftops. Lead was used a lot before people realized how dangerous it was. This guy, Albert Christophe Die, he once swallowed 21 grams of lead acetate. It didn't kill him, but it made him ill to the rest of his life. And also Ludwig van Beethoven probably died of lead poisoning. All his symptoms, rages, hearing losses, all very matching very well with lead poisoning. And I think analysis of his hair has also shown a lot of lead in his hair. So this was already happening when lead was already outlawed, but it could not be detected. But modern analytical chemistry will find it. So nowadays we are safe. Chemistry has reached such a level of analytical detection that you cannot adulterate anymore with such substances. So what we are doing nowadays, we have more artificial sweeteners. For instance, another one is saccharin. Saccharin was discovered by accident in the lab of a chemist called Ira Remsen. So this is an interesting story. This guy, Konstantin Fahlberg, is a German sugar chemist. And he was working in the US, and he was an expert for a court trial where they wanted to check a shipment of sugar which was probably adulterated, and he got the job to test it. He did this in Ira Remsen's lab, and while he was waiting then finally for the trial, he had some time on his hand, and he asked Ira Remsen whether he can partake in his research and do something with his time. And Ira Remsen coached him on this reaction. They wanted to make this compound here, this is an acid group, so they wanted to here with a common organic oxidizing agent, they wanted to oxidize this methyl group, but it didn't work. So then he suggested to Konstantin Fahlberg to try a different route and do this. And what Konstantin Fahlberg got was this compound, which we know is now saccharin. And he didn't get the product they wanted, something different. So it was an accidental discovery while working under the guidance of this Ira Remsen. So what he tells, this is an interesting paragraph, after working the whole day industriously at the lab of Johns Hopkins University, I washed my hands thoroughly before going home and was convinced that I had done my job. I was surprised that during eating, as I put the bread in my mouth, my hands tasted sweet. I suspected the housekeeper to have unexpectedly sweetened my bread and demanded an explanation. There was a short battle with words from which the housekeeper emerged victoriously. Yes. Not the bread, but my washed hands tasted sweet. I was surprised on further contact with my tongue. Also, my arms tasted sweet. I brought them home from the lab like that, from work. So I ran back to the lab, tasted every beaker, every glass, every bowl on my desk until I arrived at the taste. Fancy that. You go to a lab, you open every test tube in every beaker, and you take a sip of it. My goodness. Anyway, he has discovered artificial sweeteners. But the story doesn't end here. They published this together. And 2 years later, Fahlberg filed a patent for it without telling Ira Remsen, which is clearly incredible. And he tried to establish a company, was not very successful, and went back to Germany. Ira Remsen found out, and he was furious. He said, I'm getting sick when someone calls his name in one breath with mine. He was really finished with him. But Fahlberg made this company here near Magdeburg, and it grew rapidly, and he started also exporting his saccharin to America. At that time, it became very important for obese and diabetic people as a sugar substitute. Actually, Fahlberg had tested this compound on himself. He ate it. He found that everything else he could detect afterwards in his urine quantitatively, and he knew it was probably safe. And then they made some safety tests. So it was becoming popular. Even Roosevelt took it because he was overweight. So Fahlberg was totally dependent on the exports to the US. But by that time, adulteration cases became public, and finally the Food and Drug Administration was founded. And there was a Dr. Wiley. He wanted to prohibit sweetening of corn with saccharin. Of course, he wanted to sell his sugar. Now, finally, there was a hearing with Roosevelt, who took it himself, saccharin. And this Wiley tried to convince him not to outlaw saccharin. Roosevelt got furious and threw him out because my doctor is giving it to me. But finally he made a presidential committee to have another analysis whether saccharin is safe. And the chair of the committee was Ira Ramsden. So he made a thorough examination of all available toxicological studies. And what do you think he found? He was, I must say, this is integrity, scientific integrity. He had all the reason to be mad at Fahlberg. He could have ruined him in there, but he didn't do it. And I think this deserves respect. This was very good. So it is harmless. But is this the end of the story? No. Here is a Coke can. Use of this product may be hazardous to your health. This product contains saccharin, which has been determined to cause cancer in laboratory animals. Where does this come from all of a sudden? Well, there was a Canadian study, and they fed it to rats. They gave them 5% of saccharin for 2 generations. This is 2.5 milligrams per kilogram per day, or the equivalent of you drinking 800 bottles of Coke or lemonade. So 800 bottles for the rest of your life every day. That's the amount of saccharin they gave them. And apparently some of the rats got cancer, but they did not really die immediately. Now we are consuming about 1/1000th of this amount, converted to sugar. If you have recommended amount of sugar, maybe 10 grams a day, imagine you replace it with 10 kilos. Okay, will you be healthy after eating 10 kilos of sugar every day for the rest of your life? No. So this is what they said. This proves more than ever that saccharin is safe, because these rats survived it. Okay? So finally, the story is out, saccharin is safe. But this thing with the cancer in artificial sweeteners is lingering on, which gets me to the food safety. So we have now a lot of artificial sweeteners. These are different ones, and completely different compounds. All of them have only one thing in common. They go on our tongue and they send a signal to the brain sweet. Why they are doing it? This is something in our receptors, but chemically they are totally different. Here is actually a protein. Here's a sugar similar compound. Here's a big one. Here's a small one. Completely different compounds. It's just a fooling of our brain and tell it it's sweet. And most of them are much sweeter than sugar. Here 550 times. This one is 2,000 times sweeter than sugar. So we need minute amounts of it in order to sweeten our drinks. And in the low-calorie diet drinks, they're usually mixing different sweeteners together to make it as close as possible to sugar, because the moment it tastes a bit different, probably because our brain learns there's no sugar, we start hating it. So, and all of these have a number here. That gets me to the last part, E-numbers. What are these E-numbers? So, the E-numbers are a list of numbers which are substances which have been tested by the European Union Food Organization. So what they are doing, this is the European Food Safety Authority. They are testing substances, they group them. This can be natural and non-natural chemicals. This can, for instance, also vitamin C is one of them, vinegar is there, all kinds of substances which we can put into food. They have been evaluated for safety and given a number. And on the labels of our food which we are buying in a store, it has to be written, and you can pull up these lists and find what it is exactly. So the European Food Safety Authority, if you look at this website, it's very interesting. I mean, they're killing you with information. but you have everything. So what in principle is done to test a chemical for safety is they're calling panels of scientists, 10, 15 people, experts, biology, medical doctors, food chemists, and so on, and they read all the studies like Ira Ramsden did, which are out there. They evaluate the study, they check whether this was reasonable studies, not like this Canadian one, and then they discuss it in a panel, and finally they make a recommendation. And then, when a food is found to be safe in testing, then they divide the amount which you can take daily by about 100, and this is what the recommendation is. Small amounts are safe. So this is what they do, and if you're interested in it, the information is really, really big, and I think I don't have a better idea how to test food for safety. If you think we had the meat, we just fried it and ate it without knowing what it is. The Romans used the lead sugar. We just ate it and they poisoned themselves. Nowadays we are testing. And of course, it is possible that someone in this committee has an interest, but they have to declare a conflict of interest. I have served in the European Union on proposal evaluations. Ethics is taken very seriously there. You have to always declare a conflict of interest. All the scientists I met took it very serious. I must say I trust them. There is, of course, the possibility of mistakes. In science, it can always be, let's say tomorrow a new study is done and new results show up. And it shows that something was overlooked. Then the recommendations will be changed. Science is a living body. We are not in a religion. We are changing our beliefs. If a new fact comes up, we have to accept it, we change our beliefs. But I think they are doing what can be done. So, on the internet you find all these things. Here, for instance, read. It is extremely wise to avoid eating food with harmful food additives, E numbers in them. So, everything the European Union does is harmful. Okay, but they're nice. Not all E numbers are bad for you. But for instance, acetic acid is giving headaches and so on. Acetic acid is vinegar. 5% acetic acid is vinegar. Of course, we are not drinking it concentrated, but this is vinegar. Here we have toxic monosodium glutamate. This is one of the 20 natural amino acids, which gives the umami taste, the savory taste to meat. It occurs in meats, poultry, fish, eggs, dairy products, tomatoes, kombu, and is an excellent source of glutamic acid. This is glutamic acid, toxic, according to the internet. So we have to be really careful. So this is my last slide. This is a food blog from the BBC. And this guy apologizes for about 15 minutes before he starts that he says E numbers are not bad. Look here. He says, I'm wondering whether I'll have a career after this airs on BBC. That is, well, it doesn't take a view you'd expect a food writer to take on the subject. In fact, the series turned out to be in many ways a celebration of E numbers. Despite what you might think, when you research them in detail, you find most E numbers are good for you. There, I've said it. I'm sorry if it upsets you. I agree with him. These are things are tested. One cannot do it in any. I have no better idea. So, last remarks. Final remarks on chemicals in food. Chemistry and food are connected inseparably. All food materials are chemistry, and in cooking involves chemical reactions. Your parents have raised you on man-made, non-natural chemistry the moment they put a steak in a pan, or the moment they fried a potato, or they cooked an egg, whatever. There are toxic chemicals that occur naturally, caffeine, nicotine, mushrooms, all kinds of things can occur. And there are many non-toxic chemicals which are man-made. It doesn't mean natural, non-natural is good or bad. And finally, the E numbers. I think we can trust them as much as possible. Of course, if new science evidence comes up, we will change our mind. So that's the last what I wanted to tell you. Thank you.
Cooking will never be the same again. We're running a little bit late. We have another activity in 25 minutes, so but maybe we can have one
is your watch questions.
It's a bit fast. I have it fast.
Okay.
So
okay, we have half an hour.
We have a couple of minutes if anyone has a question. The rest of you, if you need to leave, please get my wife.
Well, If you're going to be leaving the meat in the fridge for 5 days, then is it a good idea to marinate it in wine or?
Well, as you have seen, the meat can be, first of all, kept 5 days in the fridge even without anything. Second, marinating, if it's, for instance, is vinegar, this is a preservative. It kills bacteria. Vinegar is actually produced by bacteria to outcompete others which cannot take acid. So this is actually a natural preservative that will make your meat last longer. So your marinated meat will be less prone to spoilage than non-marinated one, and on top it makes it more tender because you have the ions, they interact with the proteins and they make the meat more tender. So I don't think there's any problem with marinating.
I have a question about fish. People say fresh fish is wonderful. Should we leave fish in the refrigerator for 5 days?
No. There are different meats have different lifetime, and fish is one with the shortest lifetime. Beef has pretty much the longest, and fish is very low. Fish also has very little collagen, so there's no need to age it. So, and it spoils faster. So fish should be eaten fresh.
Anyone else a question here? Will we become vegetarians?
Some are already.
What about organic food? Should we, here
Well,
in Turkey, when we say organic, should we trust that?
Well, this I don't. Whether you can trust it, I have no idea how they're controlling it. Organic means, in principle, that you are using no pesticides. Pesticides can, of course, they are poisons and they can be poisons, but it depends on which one. It depends on in which amount and at what time it is applied. So I think there are rules for it. For instance, that it has to be several weeks before harvesting, and then there wouldn't be pesticide. But if it's, for instance, somebody is not obeying the rules and sprays the stuff with poison shortly before harvesting, then you might eat it. And so it depends always. The other thing is what organic farming, usually they use no chemical fertilizers. I don't see any reason for that. Chemical fertilizers are not a problem. They're just giving the nutrients to the food. But the pesticides are an issue. But they have to apply it. If they apply, they have to be applied in the correct way. But of course, I mean, if we don't apply pesticides, then you might lose the whole crop and we will have a famine. It has happened to the potato blight in Ireland or so. So nowadays we can prevent this, you know. So we have to be a little bit careful, but of course, definitely we should not eat the pesticides. And whether in Turkey they're controlling organic very well, I think everyone tries to cheat on these things. I know it a little bit from Germany. Of course, they can sell it at higher value, at higher price. And if you can produce cheap and sell at higher price, it's tempting. So where there are humans, they are trying to trick. And how good the controls are, I don't know.
All right, so that's a question.
You mentioned that cooking can cause cancer. Is that related to all fried foods?
The cancerous substances will be produced the more, the hotter, and the longer the food is heated. So if you want to avoid, lower temperature cooking is better. You could, for instance, instead of frying or barbecuing clearly when fat drops into the coals and comes back, there are cancerous substances. But it looks like it's not killing us, right? We are eating it very often. But yeah, there are such substances. There are studies that certain vitamins, B vitamins, can actually scavenge such cancerous substances. But you know, the food chemistry is very, very complex, and research is going on. There are many things we don't know. But definitely, yes. Also, there was the story when you deep fry acrylamide and so on, nitrosamines. These are happening when we put nitrites. So there are certain substances which are known in animal tests to cause cancer. But if they are present in very small amounts, we will not die of it immediately. And I mean, for instance, cured hams. Cured hams contain some nitrosamines, probably also some formaldehyde. Both of them not very healthy. So people say one should not eat too much of it. And as I said, avoiding very hot frying if you want to be on the safe side, that would be the right thing.
Okay, let me thank Professor SALZNER again. I'd also like to thank the members of the library team, Ulrike, Ulrike and the others who worked very hard for all these lectures. We should be back again in the new year with more lectures. Okay, thank you very much.